Okay, so what this equation means is that this compound, this molecule, um, could react with this thing here, this atom maybe, and produce this compound. Oh, and that's and that should say B, and this element here. However, in doing so, once there are some of these would react together and go back to the original product. So we've got a reaction that happens both ways. So we call it a reversible reaction. Slightly misleading because it suggests that you can make it go back, but it actually goes back on its own. So the arrow, this weird looking arrow, is saying when these go to react like that, these already start going back the other way. So really, the reaction is never complete. Let's imagine we had lots of these. So we'll shrink this. Let's make the border a bit thinner as well. So we've got loads of these, and just all over the place, right? And if you watch them for a little while, they'll whiz around and they'll start banging into each other, and we'll end up with a. Okay. We'll end up with A joining to C, and then like this, right? So this is going to start to happen. But in doing so, we know it goes back the other way, so A is going to go back to B. Or maybe it goes to a different B, like that. And then they're going to get the forward reaction, like that. And then we're going to also get the backwards reaction, like that. So both of the reactions are occurring. We've got the A B going to C, and we've got the AC plus B. Well, AB plus C going to AC plus B, and we've got AC plus B going to AB plus C. So maybe we could represent this even more simply by just going that becomes this. I'll just get like a different color. So let's imagine that we had, oh, that's a bit too small. We got loads of these now. Ooh. And they'll start to become the product. I've chosen some very similar looking colours, so maybe I could pick a different color so we can see more clearly what's happening. So we've got so some of the reactions have changed into the products. Maybe another one of these changes as well. But while that's happening, one of these changes back into the reactants, and then a couple of the reactants change into the product, and then two more, maybe three more. The products change back into the reaction, change back into the reactants. So we've got this changes to that, and that changes to that, and it never really stops because there's never a point at which it's finished because the forward reaction is happening and also the backwards reaction is happening. Now, however, if we imagine how this would change, like imagine the concentration, how would the concentration change with time? So to start off with, in my example here, we had these ones here, which we can call the reactants. It's a bit of a weird word to use because technically, if this is reacting as well, then we could say that's a reactant. But because I've written it from left to right, then the ones on the left I call the reactants, and the ones on the right I call the products. We don't normally say that products are producing the reactants. That doesn't make sense. But in reversible reactions, we can start talking like that. So if we wanted to know how the concentration of the yellow ones are changing over time, at the beginning, the concentration is going to be high. There's going to be nothing but this yellow stuff. So it's going to be a high concentration. And the rate of the reaction is going to be very high because there's nothing but reactants. So because the rate of the reaction is going to be high, then in fact this one's going to be concentration, and this one's going to and time, and then we'll also do. It's a bit messy, isn't it? I'll use the line tool. And we'll also do rate of reaction. Let's do rate of reaction as well. Against time. So once again, the rate of reaction for the yellow ones will also be high at the beginning because there's such a high concentration of them. Then there's going to be lots of opportunities for reactions. Because it's high, then they're going to drop off pretty quick. So this is going to reduce in number quite fast at the beginning. And now we're down to a lower amount, then the rate of reaction will be lower as well. So that's going to drop. It's going to even out. So like that. So we're going to get down to a particular concentration. Now, at the same time, we're going to have. So yeah, we'll come back to this graph in a moment. Actually, I can finish it now. So that flattens out like that. At the same time, the green ones, well, in my example, started off at no concentration whatsoever. There's none of them there at the beginning. But because the rate of reaction is so high, they very quickly increase in number. But then, as they increase in number, they start to decrease in number, and because they now start to be able to react with each other, and there's less yellows to react as well. So that's going to go like that. They don't necessarily intersect or cross over. It could look okay. It could go like that, but the point is they do level out. They do get flat at the same time. Okay. Now, with the rate of reaction will always meet like that because it's only going to be flat once the rate of the forward reaction is equal to the rate of the reverse reaction. So we call this equilibrium. So the reaction has not finished; it's still continuing. However, the concentration is no longer changing because the rate at which the forward reaction is occurring is equal to the rate at which the reverse reaction is occurring. So as the amount of products increase, the rate of the reverse reaction increases because now reverse. So I'll just go back to my example again. So some of the products are being produced. Now it's possible to have a reverse reaction. At the beginning, there was no reverse reaction, so the rate of down here, the rate of the reverse reaction was 0 because there was no products to go to do the reverse reaction. Now we do have a few, so now the rate of that reaction could increase until we have a few more, and now it could increase even more. Now it doesn't. If it was that either reaction is just as likely to happen as the other, then it's going to reach equilibrium when they're at a sort of 50-50 concentration. So when the concentration is equal to each other, then it's going to reach equilibrium at that point. But that pretty much never happens. There's always going to be a point at which the concentration is where either the reverse reaction or the forward reaction is favored. In other words, it's easier to have the forward reaction or it's easier to have the reverse reaction. So that's why we have the plateau, the flat bit, occurring not at the same place. Again, like I say, it could be like that, or it could be like that. It could, in theory, also meet, but that doesn't. Situations need to be perfect for that. So So that's a brief introduction to reversible reactions. I'll just stop the video, then we'll look at how we can actually affect what we call the equilibrium point.